Here in example 2, we are going to find the surface area here from revolving x squared plus y squared around the x-axis between -1/2 and +1/2. So -1/2 here, that determines a point on the graph here. This is the upper half of x squared plus y squared. So that's really what we're rotating. And then the point determined by +1/2 here. So we're going to take this segment here and rotate it around. Well, why don't we just go ahead and rotate the entire semicircle around. So when we do that, we're going to get a sphere. So that's going to look something like this. There we go. And if we follow these guys down here, then what we want to find the surface area of is this strip that goes down the middle of the sphere. So that's this strip right here. So that's a picture of what we're finding. So we want to know, what is that surface area? Well, there's two ways we could do this. We could solve this for y, get y as a function of x, or x as a function of y, or we could just use implicit differentiation. I'm going to use implicit differentiation. So let's go ahead and grab our surface area formula here. So surface area, remember, is the integral of 2 pi f of x root 1 plus f prime of x squared. So if we write this in terms of our function here, it's going to be integral e to b 2 pi, and then f of x is the same as y, and then f prime of x is the same as dy dx. So this will be 1 plus dy dx, or y prime, if you want, squared dx. So I guess to fill in the y here, we actually do have to go ahead and solve. So bring the x squared over as a negative. Y squared is 1 minus x squared. And then y would be the square root. Actually, we might get away without solving. So that's what we would get if we solved. We'd have to differentiate that if we wanted to use our first formula here. But let's go ahead and plug in here. So we've got integral. Let's see, a to b would be -1/2 to +1/2. Those are our x values. 2 pi. I'm just going to leave it as y there for a second. And then square root 1 plus, and then y prime. So let's do implicit differentiation here. So we've got x squared plus y squared equal 1. Differentiate the left. So that's going to be 2x. And then the derivative of 2y, that's a function to a power. So 2 comes down times y, first power, and then derivative of the inside, which is y prime, and then 0 on the right-hand side. So we want to bring that 2x over as a negative. So 2y, y prime is equal to -2x. And then divide both sides by 2y. So let's see, 2y's cancel there. We get y prime equals 2's cancel here, -x over y. So our y prime in here, -x over y. That gets squared, and then dx. So this will be integral -1/2 to 1/2 2 pi y, and then square root 1 plus, and we square negative x, we get x squared. We square the y on the bottom, y squared, and then dx. And then let's get a common denominator between these. So we can go ahead and factor our 2 pi out if we want here. So 2 pi on the outside, integral -1/2 to 1/2 y, and then this will be square root. The 1 we can write as y squared over y squared. So we've got y squared over y squared plus x squared over y squared. That's a common denominator, so y squared plus x squared over y squared dx. And then that's 2 pi on the outside, integral -1/2 to 1/2 y. And then here, y squared plus x squared, well, that's 1. So this is going to be square root of 1 on the top, and then y squared on the bottom. And then that's integral dx. And this works out nicely because the square root of 1 over y squared is 1 over y. So this is just 2 pi integral -1/2 to 1/2. We've got a y. And then this is 1 over y. And we're integrating dx. And the y's cancel. We're just doing the integral of 1. Well, that's no problem here. So we got a 2 pi out in front. And a derivative of 1 with respect to x is x. And we are evaluating that from -1/2 to 1/2. So this will be 2 pi. Plug in 1/2, plug in -1/2 and subtract. So 1/2 minus -1/2, which will be 1/2 plus 1/2. Double negative makes it positive. That's just 1. This is 2 pi. So that's our surface area of this strip in here is 2 pi. And let's think about this for a second because this is kind of cool. So this surface area in here is 2 pi. That's area. And then what's the surface area of the entire sphere? So surface area of a sphere is 4 pi r squared. And the radius of this sphere is 1, right? X squared plus y squared equal 1. So 4 pi times 1 squared, which is just 4 pi. So the entire surface area there is 4 pi. And that strip down the middle here is 2 pi. So that means we've got 2 pi left between the two ends, right? 4 pi is our total minus 2 pi down the middle. That leaves 2 pi left. These end caps are the same. That means that this area here is pi. And this area here is also pi. So what that's saying is, well, if we were to, divide this thick strip down the middle, if we divide that thing up here, divide it in half, like this, that this strip then here would be pi, and this would be pi. 2 halves are the same to make our 2 pi total, and then pi for each end cap, and that makes 4 pi for our total surface area of the sphere. So that's really kind of cool because this is saying, hey, if you take a sphere and you chop it in quarters linearly along the x-axis, that you divide the area into quarters equally as well, which is kind of counterintuitive because I look at this and I think, oh, wow, this big strip around the middle, that doesn't seem like that's as much area as the end cap. It seems like this area would be bigger. So that's really kind of cool that ends up that way. And then this shows you how sometimes you can use implicit differentiation, and that saves you having to do a messier derivative here. We got our x squared plus y squared equal 1, and all of our y's canceled out. So that was really nice.